Okay, so consider this 3D body rotating about an axis passing through the point C, which is moving as shown in the figure. So this C is moving with velocity Vc bar. Its position with respect to O is given by Rc bar. The position of this point Pi with respect to C, that is given by R bar I dash. So that means that the position of Pi with respect to O will be given like this, and once we differentiate this equation we get this equation. Also this theta is the angle which Ri dash bar makes with the axis. Then using the work energy theorem, we will write the small elemental change in the work done on this body due to all the forces, which is basically the summation of the forces multiplied by the distance in which they were moving. Okay, so this is basically the definition of work. Then using this equation, we can write it as this blue part plus this yellow part. So this blue part is basically the rotational kinetic energy, and this yellow part is the translational kinetic energy, and we will just prove how that is actually correct. Okay, then this work done should be equal to the change in kinetic energy of his complete body because of the work energy principle. And here in the forces we are including all kinds of external forces on this body, we are not including internal forces though. So the kinetic energy change, that is this thing, basically the change in the kinetic energy of each of these particles. So we can write it like this, once again using this equation, which then can be written as these separate things. So this red thing, we will try to prove that this is 0 when C is the center of mass, and this green thing, this corresponds to the rotational kinetic energy, and this purple thing this purple thing corresponds to the translation kinetic energy. Okay, so let's deal with these things individually. So first the yellow part, so it's the summation of Fi bar dot drc bar. So we can write this F as mass into acceleration for each particle, and then acceleration is basically the derivative with respect to time of the velocity. And then using this definition, we can write it as the summation of mi dvi bar dot vc bar, and since vc bar is a constant for this particular summation, we can take it out. So this is going to be vc bar dot summation of mi dvi bar. Okay, which is vc bar. Wait, that should be correct, right? Yes, that's correct. Sorry. So where was I? So this is vc bar dot summation mi dvi bar. Yes. So then using the definition of the center of mass, we can write this as vc bar dot d of summation mi and the velocity of center of mass. Okay, so this is the new modified form for this yellow part. Then we go to the purple part, which is the summation of half mi dvc squared, and this is easy, we can write this as summation of mi vc bar dot dvc bar. And here basically I use the fact that this thing and this thing will be equal, and that's quite easy to prove, but I will post a proof about that too. Okay, then we come to this, whatever this color is, that part. So this is summation of half mi dvi bar vi dash squared. Okay, and then basically this is the rotational kinetic energy, so it will be obviously correct if we present it in terms of omega, which is the angular velocity. So presenting it in terms of omega and the distance of point P from C, which is Ri bar, we can write it like this. And if you notice, this summation is basically the definition of the moment of inertia with respect to a point. So this is the moment of inertia with respect to the point C for that body. And then omega can be written as d theta by dt. So from there we get this this whatever this color is. I guess this color is green, whatever. So this is supposed to be IC alpha d theta. So d theta alpha IC. Okay, next we are coming to this blue part. So summation of fi bar dot ti dot tr I dash bar, and these notations are really hard to speak. Anyway, so I also did a similar kind of thing in the last proof which we did for a rotating body, but which is not moving. So like it's pure rotation. So we did the proof for that, and you can watch that if you want to. So basically the whole thing is revolving around the idea that d ri dash bar, this is perpendicular to the actual vector, which is ri dash bar. And so this theta bar, this basically represents the unit vector which is at pi by 2 anti-clockwise angle from this vector ri dash bar. Okay, so then we can write it like this, and then this complete thing is basically the net torque. So you have to use the same method that I did in my last proof. Then we come to this red part. So this is particularly simple, d summation of v bar dot mi vi dash bar. So yeah, once again we just use the definition of center of mass to get this done. So now we have all the modified parts, and putting them together we get this equation. So now if we let C be the center of mass of the body, then V dash COM bar, that will be 0, since R dash COM bar is 0. So just taking a derivative, that will be 0. So from that we can say that this red thing will be 0 as we wanted. And since VC is VCOM, just putting that into these things, this yellow and purple thing, we get that these are actually equal. So from that our equation becomes torque net with respect to COM d theta equal to moment of inertia calculated with respect to COM times alpha d theta. So cancelling the d theta from both sides, we get this thing. And yeah, that's it. This is the equation that we wanted. So here the thing is that this only works if you have the center of mass as the point with which you are taking the moment of inertia and torque and everything basically. So with other points this may not work correct. So yeah, that's it. Enjoy.